Hi guys, welcome to my video. In this video, we're going to start where we left last time with the probability density function for the t distribution. And what my goal is for this video is to just give you a demonstration of how this is actually used to calculate probabilities given some particular t statistic. Okay, so in this example of what I want to do today, we want to suppose that we have a sample. So we've got some random sample from a normal population, and we calculated our t-score, which of course is given by this expression, and we got 2.13. Okay, so here's our t-score. And what I want to calculate is what is the probability that we will get this particular z-score. So what's the probability associated with this z-score? Okay, so remember that when it comes to continuous random variables, our probabilities are calculated by taking the area under the curve of the probability density function. And if you remember from calculus, how do we find the area under a curve? We have to integrate. So in other words, what we need to do here is we need to integrate from negative infinity to 2.13. We need to integrate our probability density function with respect to t here. Okay, and what is this? This is actually our CDF, right? And this is going to give me the probability that t is less than or equal to this particular t value. Okay, and so this is how we get, our confidence intervals for t-scores. This is how we can determine whether or not we're accepting or rejecting a null hypothesis. No, I'm sorry, did I say accepting? No. No. This is how we can determine whether we're rejecting or failing to reject a null hypothesis based on a t-score. Okay, so here in our example today, let's say I've taken my sample, I've got n equals 16, and my t-value that I want to, my t-value that I've calculated is 2.13. Okay, so that means I've got degrees of freedom equal to 15. All right, so let's go ahead and go through this. Turn this off. And first of all, I have entered this. So I've got the probability distribution function here in Wolfram Alpha. Great. Wolfram Alpha is great, by the way. And there's, you can see there's some slight variation due to a further algebraic simplification than I carried out. Okay, so you can take what we just saw on the previous screen and you can manipulate it to this. So this is what we're going to be using. And so what we need to do here in order to calculate the probability of having our particular t-score, we need to replace the n with 15, and then we need to integrate on the interval from negative infinity to 2.13. And so I have that here in this screen. Okay, and so you can see here, what have I done? I have, let's see if I can make this any bigger. It's already really huge, but okay. Yeah, that's a lot bigger. Move one thing. So what I've done here, you can see, is I'm integrating the PDF from negative infinity to 2.13. That's my t-score that I calculated, right? And then I replaced my degrees of freedom here. I replaced the v with my degrees of freedom into the PDF here. And according to Wolfram Alpha, when I integrate this, I get 0.97, 0.975 if we want to round it. Okay. And so what that means is that where this t-score is at on my distribution, 97.5% of all values will be below it. Okay, so that's exactly what we have just calculated. We calculated the area under the curve from negative infinity, which, don't worry about that. I should say from negative infinity to 2.13, the area under the curve is equal to 0.97. But as you may have seen, or as you may know, or as you should know, or should learn, is that when we're calculating probabilities of continuous random variables, we can equivocate their probabilities with the area under their probability density function. And so in fact, this is, this is the value of the CDF at 2.13, 0.97. So what does that mean? It means that if we look here, that this would be my T, this is my T distribution. Okay, so this is what when we graph that monstrosity, that actually is not a monstrosity, it's actually quite beautiful. When we graph that beautiful probability density function, we get this nice bell-shaped curve. And here is where the T is equal to 2.13. So it means exactly this. Let's see if I can draw some things like here. Yeah. It means that all of this area from negative infinity to this point is 97.5% of the area under that curve. And so over here, how much area is over here? Well, over here, we've got 0.025. Okay, because remember, actually, I'm saying percent, right? But we all know, or maybe you don't all know, but it should be the case that for every PDF, if we integrate any PDF, it should always be equal to 1, which corresponds to the fact that, it's a sample space that has normalization. So it should always be this. This should always be the case, at least as far as I'm aware of, right? And if it's different than that, then there's something I don't know, which is totally possible. All right, so here is 0.025 area, and actually the area is actually just like 0.975, right? So 97.5% of the area is to the left of 2.13. And so above that, anything above that has a 2.5% probability. Okay, so this is the idea behind the area and the probability. We have to use the area. Why do we have to use the area? Well, you've probably seen this in probability because we're dealing with continuous random variables. Continuous random variables are real numbers, and real numbers have levels of precision that can be infinitely increased. Yeah. Okay, let's say it like that. All right. And so that's why we have to use area. All right. And then now let me show you one thing. If I go to look at a t-table here, which I'm going to do now, we can find this value. So I'm going to look at my t-table over here. So, all right, it should be on the t-table. So over here, I've got my t-table, and I just want to show you one thing here. So we're going to go down to 15 degrees of freedom. That's going to be here. So there's my 15 degrees of freedom. And then remember that area, we said 0.025. Okay, so that's going to be 97. So that means that to the right of this t-score, I'm going to get 0.025. Okay, so you can see that according to this. All right, so actually this table is finding the critical t-star values. Okay, so it means that the t-score that corresponds to degrees of freedom and 15, and to the right of that being 2.5% probability is exactly 2.13. Okay, so what if I want to find a 95%? So I want to do a two-tail test, so then I would go over here. Actually, I would just go like this. Let me just change my screen. So I'll go over here, and we can look at this graph here. Oops, no, we can't. Okay, so now in between these two, actually, is that going to be right? Yeah, that's right. So in between these two will be 95% of the data, or 90. So the 95% of the area. So over here we know that this area is 0.025, and this area is 0.025. Okay, so this is negative. So it's symmetric, right? That's one of the beautiful things about it. So this is negative 2.13. This red line here, and this red line here is positive 2.13. So it means that in between these two vertical lines is 1 minus 2 times 0.025, of the area. So in other words, it's 1 minus 0.05 of the area, I think so, which would be 95%. Okay, so if my t value happened to land in this region in the middle, then it would be in what we would call the fail to reject region, given that if we're doing a hypothesis test with a 95% confidence interval. And if my t value happened to be over here or over here, then that would mean that the probability of it being from, well, a normal distribution or from this, but it would mean it would be a rare event. Okay, let's say it like that. So that this would be our region where we would reject the null hypothesis. And this would be the region where we would fail to reject the null hypothesis. And so that's just some intuition, I hope, about how we're calculating probabilities and how the t-scores are corresponding to the probability. So the t-score is it's just like a z-score. We're standardizing the mean value in a sense, where here the center is 0 here, and then we go 2 to 4 like this, and so each location here corresponds to a area under the curve, right? And so that's how we can calculate probabilities, because the area under the curve is equivocated with the, I'm not saying equivocated, I think I'm using that word wrong. I think equivocate it does not mean what I'm trying to say it means. I think equivocate means like when you are backpedaling or something. But what I mean to say is equivalent. Sorry, I've only had 1.5 cups of instant coffee. My bad. So what I meant to say is equivalent. The probabilities are equivalent to the areas. All right. So that is it for this video. I hope you can accept it, warts and all, and that you got something good out of it. And if not, if you notice any mistakes that I didn't mention myself, please post those in the comment. If you have any suggestions or so forth, please also post those in the comment. Thanks for watching, and hope you understand it a little bit better than before. Bye-bye. In the next, oh wait, let me tell you about the next video. So in the next video, I'll show you, we'll do some problems and we will calculate everything manually, okay, except for, we'll use the t distribution table. And then finally, in the video after that, we'll do the Python implementation. Okay, thank you. And I hope this helps.